showing and presenting us your thesis into the seismic response of pile-supported wharves. 25 to 30 minutes at most.
Thank you. So again, my PhD thesis is titled Insights into the Seismic Response of Pile-Supported Wharves Subjected to Liquefaction-Induced Ground Deformations, Implications for Design. My PhD thesis was supervised by Professor Karlo Lai and Professor Mieszko Szyrinowski. So this is the outline of the presentation of today. So first, I will walk you through the relevant case histories of wharf failures and the implications for design that were recommended after those case histories and in the past 30 years, and how those recommendations, they still lack more details about the combination of inertial and kinematic loads for the design of piles when found in liquefiable soils. So that will be the motivation. Then I will move forward to explain my methodology and the analysis that I conducted on a wharf structure located in southern Italy, in Gioia Tauro. So this wharf structure, this analysis will serve as the baseline for explaining the reasoning behind what I propose, two new design verifications with respect to two different loading cases that represent the evolutionary nature of the problem when liquefaction-induced ground deformations are relevant. This is done by means of 2D fully coupled nonlinear effective stress dynamics of structure interaction analysis. That's a bit of a mouthful, but in summary, what it means is that the behavior of the liquefiable soil is accounted by the modeling approach, as well as the nonlinear response of the pile structure and the wharf with respect to the case of Gioia Tauro. And that will open two questions. One is regarding the accuracy of the methodology, the numerical methodology in capturing lateral spreading ground deformations. And then I will take you to New Zealand, to the port of Wellington, to explain how this methodology is able to capture the lateral spreading ground deformations that were observed during the 2016 Kaikoura earthquake. And after that, I will come back to Gioia Tauro to incorporate a new dimension into the complexity of the problem and trying to convince you about this idea of accounting for the evolutionary nature of the problem by considering two critical loading cases, by including the ground motion variability. And finally, I will finalize this section with a comment or with a development of the results and the insights gained from a global sensitivity analysis. And then I will finalize with the final recommendations that are the result of my study and recommendations also for future studies. So first, pile-supported wharves. This is more or less the timeline, the timeline of the most relevant earthquakes that have triggered wharf failures in the past 40 years or so. So starting from the Loma Prieta earthquake in 1989 and the Great Hanshin earthquake in 1995 in Japan. So here you have pictures of two important wharf failures at two different cross-sections of the piles. First on the left, which is the failure caused by the Loma Prieta earthquake at the port of Auckland. The port of Auckland suffered massive, extensive and severe liquefaction, but what you are seeing there is the damage of the cap of batter piles. Batter piles are inclined, so the damage, the cross-section that suffered excessive damage was the section located connecting the deck and the piles. And what happened in Osaka is that at the port of Kobe, the port of Kobe is a land reclamation, so it's man-made. Those are fields placed by hand dumping or hydraulic fields. They liquefied, and severe liquefaction was triggered throughout the entire island, and that caused lateral spreading ground deformation that pushed all the water into the sea. And what you're seeing here is the cross-section of one of the damage. And the most severe damage was observed at the in-ground sections of the pile, so more or less 9.6 meters below the grade. And this kind of damage was really difficult to repair. All this wharf has to be replaced, and all the piles have to be extracted from the soil. It was very costly. So after this, the regulation suggested two things. First, avoid battered piles. Second, avoid severe damage at the in-ground cross sections. Then we have another case histories. For instance, the 2010 Haiti earthquake that completely damaged the city of Port-au-Prince, and also the Kaikoura event that I will tell you more about with respect to the case of Wellington. But what does this imply in terms of seismic design? So we have in the pioneering work 2001 by Piank, that was the first regulation that recommended the consideration of kinematic loads and inertial loads in combination. And then the past 20 years have seen more developments in terms of display, the performance-based design and strain limits and performance limits. But what is important is that the newer recommendations, the newer seismic guidelines, they provide the recommendation with respect to one particular type of analysis, the beam on nonlinear Winkler foundation analysis. And for this type of analysis, the guidelines refer us to the kinematic loads are the loads that come from the permanent ground displacements, and the inertial loads come from the inertial movement of the deck. And I will try to convince you throughout this presentation that this interpretation is not compliant with the evolutionary nature of the response of liquefiable soils. And as a result of what the recommendations suggest, they suggest to combine these kinematic and inertial loads, and there is no agreement into the combination, the combination factors, and there is not even agreement into what is the adequate assessment methodology for these loads. So the research objectives of this thesis were twofold. First was to underscore and assess the key features of the seismic response of large diameter pile-supported wharfs, and to test the current assumptions behind the design methodologies that are suggested by the seismic code provisions. That will be with respect to the port of Gioia Tauro in Italy. And how did I do this? I did this again by means of effective stress nonlinear soil structure interaction analysis, and by accounting by the epistemic uncertainty regarding the soil modeling, the soil modeling of liquefiable soils. So I used two different constituents, and SDM. Both models have been extensively validated against centrifuge modeling, against empirical relationships, and against case history, in particular for the case of SDM with respect to the 2010 and 2011 Christchurch sequence. Now, the other research objective is regarding the adequacy of this analysis methodology, and I tested this with respect to the Port of Wellington in New Zealand, and I will show you more details later on. So first, the seismic response of large diameter pile-supported wharfs, the case of Gioia Tauro. So what you're seeing in your screens, in the screen on the left, is the port of Gioia Tauro. It's an excavated channel. That is a difference with respect to the other ports in the Pacific Basin. This port is excavated. The other ports were built on top of land reclamations. So the diameter of the piles of the wharf are around 1.5 meters. 4 rows of piles spaced every 6 meters. And from an extensive CPT campaign, I developed 2 different representative geotechnical models for the site. The soil deposit at the site of the port is almost entirely comprised by coarse grain materials, so sands and gravels of different density. But in some cases, after they excavated the port most likely, they also had the need to place fields in the side of the port. So the other soil profile that we see on your screens pertains to the soft sites that characterize these fields materials. So the most important thing for the native deposit on the left, the native deposit of the first 30 meters, the first 20 meters is comprised by 3 characteristic units. The unit in the middle is quite dense, so I refer it as a non-liquefiable layer by resistance, but by composition is a coarse sand, so it can liquefy in theory depending on the demand. But the critical layer is the critical layer between 12 and 20 meters with a QC1 NCS values 135, the layer that is colored with yellow in that picture. So in terms of the analysis, I conducted 2D fully coupled analysis with flag. So the liquefiable soils that are shown in green and yellow were modeled with either PM for sand or SDM. The nonlinear response of the piles was also accounted by means of the distributed plasticity model of Andreotti and Lai 2017. The mass of the crane, so the effect of having the crane on top of the deck was also included by lumping the mass on the crane on the deck. And also importantly, the lateral boundaries were assigned with the free field boundary conditions in the classical sense. So this important thing about this analysis is that it moves forward the level of detail in this type of modeling, because usually in geotechnical engineering we are very good at, or we can be very good at modeling the soil response, but then the piles are assumed elastic, and then in a structural engineering there are very details in modeling the superstructure response while not being as in detail with the ground response. In this case, the methodology is subdivided into 3 phases to account for 3 different conditions. So first, to isolate the effect of the wharf against the lateral spreading ground deformations, I developed two models. One model that considers the presence of the wharf, which is the soil structure model, or SS model. One model that doesn't consider the presence of the wharf, which is the free field model. And for those two models, I used three different input intensities, so three different input excitation at three different PGA levels. And times to that, I also use PM for sand and SDM in parallel, and to do a systematic evaluation for the effect of the wharf structure, the input intensity, and the epistemic uncertainty regarding the soil modeling. And that gives me 24 to the analysis, which will constitute the baseline of this study. Now, the question about how to calibrate advanced quantitative models, they are calibrated with respect to the liquefaction resistance curves provided by Idris and Bull and Jay 2014. This is in absence of laboratory test data, but in any case, if laboratory test is available, the methodology is the same. Try to target liquefaction resistance curves, to check for K-alpha effects, to check for K-sigma effects, and this is important. K-sigma effects relate to the effect of sustained shear stresses. So you know, in a slope, you have sustained shear stresses from the static conditions, and K-alpha effects reflect that effect on the cyclic resistance of the soil. In this case, SDM is providing larger values of cyclic resistance with larger sustained shear stresses, but most importantly, the key difference between the two models that we propagate throughout the analysis relates to the strain rate, the cyclic strain rate. When I mean cyclic strain rate, with respect to this analysis, you are seeing on the first plot on the bottom, you're seeing time histories of, you are seeing shear strain versus number of cycles. On the top, you're seeing excess per water pressure ratio over number of cycles. When excess per water pressure is equal to 1, you have liquefaction. So liquefaction is triggered at the same number of cycles for both models. But for SDM, the strain level before liquefaction is higher than PM for sun, is slightly higher. And after liquefaction, what PM for sun is resulting in is a larger strain level than SDM. Those are the key features of the two models. And let's see how they propagate in the 1D analysis. So just let's focus on the image on the left. The left is the profile of what I call the lateral displacement index, is the integral of the maximum cyclic shear strain. It should be called differently though, but let's say LDI. Let's focus on the evolution of LDI. SDM is persistently giving larger values of this response parameter, and I will show you that that is in contrast to the 2D response, so let's keep that in mind. So these are the difference between the two models, difference in terms of a strain rate before and after liquefaction, and how that propagates in 1D modeling. And in terms of 2D response, we have here results in terms of residual displacement. So these are the final lateral displacements after the input motion was applied to each of these models. From top to bottom, the input intensity is increasing. Left is PM for sun, right is SDM. What we're seeing there is evolution of two different modes of failure. First is the toe failure. So you see that strains or displacement in this case are generated at the toe of the slope, at the base of the slope, and they propagate with input intensity, but most importantly, lateral spreading is evolving even faster for PM for sun than SDM. So in 2D, we have that than PM for sun is even more critical response compared to SDM. So to give you an idea, this is a fairly coarse, medium to dense coarse grain sand, and PM for sun is indicating that the residual displacement is almost 1 meter, whereas SDM is indicating that the residual displacement is 60 centimeters. And this is because there is a clear distinction between the cyclic and post-liquefaction phases of the response, and I will develop the idea later. So here it is. So time histories again, on the bottom, excess per water pressure ratio, on top, shear strain. So you see that on the right, we have the 1D column. So a strain level on the 1D column are fairly comparable for the two models. And liquefaction is triggered at the same instance. But when you see the backlands of the 2D response, you see that during the cyclic phase, that is enclosed by the dashed lines, PM for sun and SDM are given comparable responses. And then after the cyclic phase of motion, we have the lateral spreading phase of the post-liquefaction phase, and that is where the results start to deviate between the two models. This an overstress of what I say is an overkill. I'm comparing here time histories of displacement on the bottom at the 1D column. So on the bottom plot is time history of displacement at the surface of the 1D column. Top plot, time history of displacement at the crest of the slope. So if you look at the green lines, they're highlighting the response during the cyclic phase of motion, more or less comparable between the two models. And then when you look at the yellow arrow, you see the response at the post-liquefaction phase of motion. Now, what does it imply in terms of warp response? So I will, because of the sake of time, I couldn't show you, but basically, the toe failure is restrained by the warp, but still the presence of the warp has to withstand the lateral spreading ground deformations. And what is the most critical pile of the warp that is fully embedded within the soil, that is the trailing pile. So what you see here is our profile of ductility ratio for the trailing pile. Left is PM for sand, right is SDM, and I will focus on two particular cross-sections. The first cross-section is the pile deck interface on top, and the second cross-section is the interface between the dense sand and the medium dense sand. So what you see at the pile deck interface is that the demand given by using PM for sand and the demand given by using SDM is quite comparable. And the different colors just highlight the different intensity levels. So for the highest intensity at the pile deck connection, PD on this slide, you see this is the response in terms of moment curvature. You see a lot of number of cycles, a cyclic response mostly. And then you see on the bottom plot the response at the ingrown hinges, one of the hinges located at the interface between the dense sand and the medium dense sand. And you see that the response is almost monotonic. And this is of that idea, of that fact. For the pile deck section, we have that the peak load, or the most critical loading condition, or the most critical instant occurs during the cyclic phase of the response, whereas for the inground hinges, the most critical loading condition happens at the end of motion, after the post-liquefaction phase of the response. So here the main insights are twofold. First, in terms of the performance of the numerical models, and second in terms of the performance of the warp. And we are left here with more or less this picture. We have this time history. So liquefaction is the green arrow. Before liquefaction, after liquefaction, a couple of cycles after liquefaction, we have the cyclic phase of motion. During that cyclic phase of motion, the peak inertial load occurs, and the shear-induced deformation attain their higher value. The shear-induced deformation refers to the deformation caused by the earthquake itself and not by the effects of the liquefaction phenomena. And then we have the effects of liquefaction phenomena. So what I'm proposing is, instead of evaluating one critical condition, which is giving a combination factor to the inertial load plus the full kinematic load of the residual displacements, two different loading cases should be analyzed. One case for the cyclic phase of motion and one case for the post-liquefaction phase of motion. So for the cyclic phase of motion, you have the full inertial load plus cyclic deformation of the ground. And for the post-liquefaction phase of motion, you have only the residual ground displacements as kinematic loads. So now let's test these ideas by first analyzing the accuracy of the modeling strategy. And this is with respect to the Thorndon container wharf and descent at the Port of Wellington in New Zealand. So this is a plan view of the Port of Wellington. Just to give you context, the Port of Wellington is land reclamation. It has been expanded during several times after the 70s. It suffered severe damage from liquefaction-induced ground deformation after the 2016 Kaikoura earthquake, magnitude 7.8, but it was also damaged during previous earthquakes, the Lake Rasmere earthquake and the Cook Strait earthquakes that happened in 2011. So this is just an example of the type of damage that happened at the port. And most importantly, we have measures of the researchers at the University of Canterbury. They have measurements of cumulative crack widths, and we can compare them with our results. So this is again a schematic of the numerical model, similar to the case of Gioia Tauro. In this case, the gravel field is considerably looser than the medium to dense sand in Gioia Tauro. The modeling approach is the same. The target relationship for the modeling of liquefiable soils are the liquefaction resistance curves derived from IDRIS and Boulanger. Total stress modeling for the base layers, free field boundary conditions applied at the lateral boundaries of the model. And these are the results in terms of final horizontal displacement on the left for two input intensities, 0.2 and 0.3 G. And on the right, you see the final response in terms of maximum shear strain, again, for 0.2 G and for 0.3 G. And just to give you an idea, the Kaikoura earthquake in a station nearby the port, it registered a PGA value of around 0.22 G. So a representative analysis in this case would be the one located on top. You can see that the maximum residual displacement in this case was around 1.2 to 1.6 meters, and when you increase the input intensity, you got residual displacements of the order of 2.8 meters. And how to compare that with measurements? So Professor Ishihara in the late 90s, after the Great Hanshin earthquake, he proposed a framework for understanding lateral spreading ground deformations. And he proposed that the lateral spreading ground deformations can be subdivided into two components: the uniform component on lateral spreading and the non-uniform component for lateral spreading. The non-uniform component is the most damaging and represents the ground displacement that takes place near the waterfront, so near the wharf in this case. And the uniform component for lateral displacements is represented by the residual displacements that accumulate back far inland from the wharf. So we have these three different damage measures or response parameters for lateral spreading. Remember that from the 1D case, what I showed you was results in terms of LDI, lateral displacement index. For the 2D case, the response parameters will be the residual displacement at the crest and what I call delta lateral, which is the difference between the residual displacement at the crest and the uniform lateral spreading displacement. Now, how did they compare with respect to the measurements? We have here the comparison in the bar plot. The gray bars correspond to different measurements of cumulative crack width along several transects behind the wharf. And you also have in the pink columns correspond to the results of the 2D numerical simulations. So you can see there is a fair agreement between our results and the measurements. When you increase the input motion, you will see, of course, a dramatic increase of the crest displacement. So far, the non-uniform component of lateral spreading displacement is being well captured by the analysis, but we have a problem. We hit a wall with respect to the uniform component. We don't have a fair agreement with respect to the measurements for the uniform component, and that means that in the near field, so near the wharf, our simulations are accurate enough, but far away from the wharf, the effect of the lateral boundaries are still affecting our results. So that's the summary of this section. We can use our results to compare what's happening near the wharf, but far away inland, we shouldn't trust so much in our simulations. Now let's go back to Joya Tauro and let's include the effect of ground motion variability. So let's use several motions to this type of problem. So what you see here is the response parameters that I selected, 3 ground response parameters. Delta lateral, which is this difference between the crest and uniform lateral spreading displacement, the crest displacement, LDI, and in terms of the wharf structure, the peak deck acceleration, and in terms of the pile, the maximum relative rotation at the pile deck connection and the maximum relative rotation on the inground hinges. What we have here is the result of a multiple stripe analysis. And left is for the case of the free field model, right is for the case of the solid structure model. You can see that the displacements go, when liquefaction is triggered, you can see a clear deviation of the two models. PM for sun is represented by the blue dots, SDM is represented by the red dots, the red crosses. And that is for the system response on top. And now let's see what happens locally to the pile. So on the left, on the bottom, you can see the same distribution, the same plot for the maximum relative rotation on the pile deck connection, and on the right, the maximum rotation at the inground sections. You see two different behavior. At the connection, it saturates and it stops increasing. At the inground hinges, it kicks off after liquefaction, and PM for sun is giving more critical values. So let's populate this matrix. What it says, let's analyze pile deck connection and inground hinges, and let's see what is critical for those sections: the inertial demand, the kinematic demand during the cyclic phase, or the kinematic demand during the post-liquefaction phase. And I did this just by analyzing the results of linear regression. In this case, it's for the inertial demand versus the response at those two sections. We see that for the pile deck section, we have a really, really good correlation between the inertial load and the critical response of the pile deck section. Not so good for the inground hinge. So we can see now how unrelated is the inertial load with respect to the critical load at the inground hinge. And this in case of residual displacements represented by the residual displacement at the crest of the slope. We have that this is very critical for the inground hinge, so it controls the demand at the inground hinge, but at the pile deck connection we are not so sure, so we have to refine the analysis here. So let's make the separation between cases that liquefied and cases that didn't liquefy. So this plot is only for those cases that exhibited liquefaction. So you can see at the bottom that the residual credit displacement is still well correlated to the critical demand at the inground hinge, whatever is not the case for the pilot bed connection. So whatever is going on at the post-liquefaction phase in terms of ground response is not affecting the demand at the pilot bed connection. And this is another, this is for the cyclic demand, the cyclic kinematic demand. So what you see on the x-axis is LDI, this lateral displacement index computed from 1D analysis that is only capturing the shear in those strains. And that correlates well for both the pilot bed connection and the inground hinges. So this is the summary. We have that for the pilot bed connection, what is critical is the inertial load, of course, and the kinematic load during the cyclic phase of motion. And for the inground hinge, the inertial demand is completely correlated the inertial load is completely correlated to the demand at the inground hinge. And what is critical for the inground hinge is both the cyclic displacements and the post-liquefaction displacements. This is a byproduct of the analysis, just a listing of the most relevant intensity measures in terms of proficiency and efficiency for different response parameters. Of course, it changes for different response parameters, but the one intensity measure that ranked among the four first was a modified acceleration spectrum intensity. So this is just a comment for future studies. This can be explored in a most robust way by considering a different way of selecting ground motions. But what is important here, again, going back to the framework, I have corroborated that yes, before and in the cycles after liquefaction, the few cycles after liquefaction, what matters is cyclic displacements for the wharf, the performance, and then you have the post-liquefaction phase. So design methodologies, they should be tailored to address the two different loading cases. What is doing now in the regulation is that you have the kinematic load is only referred as the load that takes place during the post-liquefaction phase, and the inertial load, according to the regulation, is that takes place during the cyclic phase. And the regulation, I recommended to combine these two types of loads that occur at two different time instants. Okay. I can escape this. This is just how to handle model uncertainties, a global sensitivity analysis. Important thing here, not only ground motion variability is important, and tip resistances of liquefiable soils, also hydraulic conductivities. When modeling liquefaction with these 2D numerical models, hydraulic conductivity plays a major role numerically. So in terms of conclusions, they are again two-folded. One with respect to the ground response and the performance of the two different constitutive models. So PM for SAN reproduces larger post-liquefaction strain accumulation than the SDM, and SDM produces more or less larger cyclic strains than PM for SAN. This is an overkill of what I just said, so I will go fast. So the recommendation is, again, to consider two critical loading cycles instead of one. And for the peak inertial load, because the modeling approach here considers the nonlinear response of the wharf, it wouldn't make sense, or it would be too over-conservative to use force-based design methodologies for the piles for the cyclic phase of motion. These are secondary conclusions about the most proficient and efficient intensity measure, the effect of hydraulic conductivity, and the fact that the modeling strategy didn't work as well for reproducing the uniform component for lateral ground displacement. And again, this is just a reminder, this is valid for 2D effective stress analysis that are aiming at reproducing lateral spreading modes of deformation. And this is also valid for large diameter pile supported wharfs found in medium to dense coarse grain materials. In terms of future work, again, two-folded, one can add robustness to these insights by refining the modeling between the interface of the pile and soil, or better, by including a criterion based on the post-liquefaction strain accumulation to calibrate advanced constitutive soil models. And the scope of the research can be expanded by testing this framework with respect to the results given by simplified analysis procedures, or again, by pursuing the other route, which is the fragility analysis, or exploring optimal intensity measures with a most robust framework. And I think I made it. Thank you, and I'll be happy to take your questions.
Thank you, Ricardo. let's move on to the questions of the committee. Vlatko.
Okay. Thank you, Ricardo. Yeah, it was really my pleasure to read your PhD work. It was a lot of things you have been done, a tremendous job. Congratulations. I'm very happy that apart from 3 other candidates that were facing structural, now we are facing something which is underground for the soil, which many of us many times neglected. So again, well done job. And I will start, I have many questions, but we can continue, but I have few of them, and I will start it with the basic and fundamental one. In your PhD numerical simulation that you have done a lot, you are focusing on displacement, okay? Anyhow, ground displacement, pile displacement, but for the ground, if we have intensive liquefaction that you were able to observe during your numerical simulation, is it true that we have to face on displacement? Because in liquefaction phase, I mean full liquefaction, the contact between the particles are completely lost. And is it true that we have to continue with the principle of solid mechanics, or we should take into consideration something else? I will directly focus. Is it good to see the relative displacements, to be focused on the relative ground displacement-based approaches and everything, or we should take consideration of something else? Because it is not ground anymore. After liquefaction, it is something else.
So what I understand your question is regarding the validity of the interpretation of the results, given that the soil is at its fluidized state. So we're talking about a fluidized material after liquefaction, and whether or not our estimates are valid in that case. I believe that the critical states of mechanics and effective stress principle provide a very robust framework for continuum analysis of the problems. Of course, then, if you go too much non-linear, you will have other conditions that this type of analysis cannot reproduce. For instance, soil ejecta, particle migration, sedimentation, and we hit a wall with what we can do with respect to the effective stress principle and continuum mechanics. But still, we are within the range of applicability to provide reasonable estimates, as you see with the case of Kaikoura earthquake, as you see with the case of Kreitzer, the Canterbury sequence, and also other centrifuge tests. So the comparison between our estimates in terms of displacements are the observations are fairly good. Of course, there are a lot of limitations with other complexities developed due to the soil type that should be accounted for. I will say that as usual, we can take aid from empirical data for that cases.
Just as a recommendation, you should also, after finishing this job, you can continue writing a journal paper, but taking into account also strain rate. So the velocity of development of the relative displacement is also very important regarding especially lateral spreading due to the liquefaction. That's
okay.
only
yeah, that's also damaging.
Yeah, okay.
Thank you.
And then the other one, you made an excellent simulation of the 2 case studies. Because it's a large diameter piles, did you notice any shadowing effect of the development of the displacement due to lateral spreading? I mean, shadowing, is it the piles itself as a structural element protect development of the soil displacement in the inner part of the wall structure?
Well, that will relate more to the 3D nature of the problem. But what I see from these simulations is that due to the trailing pile, if you see that the trailing pile is, even our 2D analysis, okay, I have to go back to so the trailing pile is not as embedded as the other piles. So what is happening? You're referring to a 3D case, but even in the 2D case, we were saying that the piles wouldn't perform as well because it's so short, the embedment is not enough within the dense sand that the tip of the pile rotates. So the whole pile moves once the rotation occurs at the tip of the pile. Note that these are large diameter piles, 1.5 meters, so probably they are displacement piles, and the reason why they didn't drive these piles deeper was practical, because they are the large diameter.
Okay, finally, it's not a question, but thank you giving us so good explanation regarding inertial and kinematic effects, which is still under debate how we should take into consideration in the design of such a structure. So thanks once again for excellent explanation about inertial and kinematic effects. Thanks.
Thank you.
Thank you. Just a very quick question, because your presentation reminded me of a practical problem, not related to wharves, but I mean, in a similar setting. And so I noticed that you used two soil models, so PM4SAN and STM. And this reminded me of a practical problem we had a while back with the design office that was simulating a large complex problem, geotechnical problem. And then there was this issue, which modeling approach to go for. And this is the question I have for you. So if you had to recommend one of these two models, because they give different results in different phases of the whole process of liquefaction, I mean, it's not practical in practice to use two and then compare. So what would you recommend to a designer?
That's very important, especially because they're very complex models. You better stick with one because it's more practical for your practice. What I would recommend is just focus on the features that the model are reproducing. Cyclic resistance is one, so the calibration was made with respect to cyclic resistance. Modulus degradation is other one, but the one I'm recommended also to take care of is the post-liquefaction strain rate. So you can still use PM4SAN, adjust the post-liquefaction strain rate accumulation, and use as much as values as you can do practically. And you can explore the effect of what happens after liquefaction. You know that at the point of liquefaction, cyclic resistance is very well, it's more or less very, very well established at the moment. So the problem is what happened after. So I would recommend to use different rates of strain accumulation after liquefaction with the same model.
So PM4SAN would be your answer.
Yes, if SDM could, I say that because I have been involved in the development of SDM, and we are still working into implementing this feature in SDM. That's why I recommend PM4SAN.
Thank you.
I will not tell this to Mishko.
Yeah, of course. Don't say that.
I would like a clarification on whether you put absorbing boundary also at the bottom. Did you include absorbing boundary at the bottom or not in the Wellington model?
In both models, the base of the model was a compliant base. So any incoming wave hitting the boundary is being absorbed by a dashpot-like boundary for both the lateral boundaries and the bottom in both models. So it was accounted for.
Okay, thank you.
Again, there is time for at least one question from the audience if someone wants to. You are all very lucky today with the questions. No one is trying to put you on to a test. Okay, thank you very much.
Thank you.
And the last presenter, Evena Sipcic. I'm not sure if this is the way I should read your surname, but did my best from Montenegro. And Nevena is going to talk to us about earthquake sequences and among other things that she will now tell you about.
Thank you. Thank you, Ricardo. Hi, everyone. So today I'm going to talk to you about what I did in the last 4 years, a little bit longer, together with my supervisor, Paolo. Hopefully, by the end of this presentation, you will learn a little bit more about the seismic sequences and why they are important in risk assessment and how can we incorporate them. So first, I'm going to talk about a little bit about the motivation and about the objective of our work. Then I will go into the separate parts of risk assessment. So I will talk about hazard, I will talk about fragility, and also about the record selection. So basically, the traditional models are based on a very simplistic concept where all dependent events are disregarded. This basically means that we identify the clusters of events in the earthquake catalogs, and we usually keep just the largest event in each cluster, which we call the main shock. So foreshock and aftershock are disregarded. This is the process that is known as declustering. So for example, if you look at the sequence that happened in central Italy in 2016-2017, you can can see that we have many events, but after the declustering, we are left with only one event, the main shock, with a magnitude 6.6, even though we had 3 events with a magnitude larger than 6. So we completely neglect these events. So you must be wondering why. Why do we do this? Why do we decluster? The initial reason for declustering was because people were thinking about design, not really risk. So they were saying, okay, if I have a structure that can withstand the magnitude 7 earthquake, then I'm fine if I have the lower magnitude events. The second reason was that people noticed that if we decluster the catalog, we are left with a Poissonian distribution, which simplifies our lives a lot from a mathematical point of view, so it was convenient to go in that direction. The third reason was in CAT modeling, practitioners would say that, okay, maybe we disregard the aftershock and foreshocks, but we do calibrate our models collecting the data, which we collected at the end of the sequence, so we are actually fine. However, we believe that the logic behind the declustering has several disadvantages. So first of all, we are not interested, we are more interested in the largest intensity rather than largest magnitude. So you can easily think of the 2 events with the same magnitude that have cause very different damage and loss. The second reason is that usually in a traditional declustered view, we assume that our structure is in the pristine or intact conditions all of the time. In reality, we usually do not have enough time between the events to repair our structure, so we can have the accumulation of damage and the reduced capacity of our structure. And third, when it comes to the CAT modeling, it's actually rarely the case that we do calibrate our models based on the empirical data. This doesn't happen often, maybe in the largest insurance companies. And even if it happens, we are using the data that is either collected at the end of the sequence or during the quiet period when we have only main shocks. So it's very hard to use this data for prediction. So it is clear that these models, the main shock only models, are not perfect. And this was shown several times in history. So in the last 30 years, we had many seismic sequences where it was reported that the damage after the aftershock was significantly higher compared to the damage that we had after the main shock. So as an example, if you look at the New Zealand in 2010-2011 sequence, the largest magnitude event, so the main shock event had magnitude 7.1. And according to Swiss Re, the losses after this event were $8 billion. But after the aftershock event, which had 6.2 magnitude, so significantly lower, the losses were actually $15 billion. And also there were 180 fatalities more. So in traditional models, we would not account basically for this. So this was noticed in the research community, and people started thinking, how can we incorporate seismic sequences? What can we do? This is relevant for several fields, I would say, and particularly recently insurance companies they are aware that they are pricing the premiums based on the risk models that underestimate the risk. So they're interested in including seismic sequences. So in our thesis, we wanted to see if we can build better models, and we focused on hazard, we focused on fragility, and we focused on record selection. So I will start naturally with hazard. When it comes to hazard, our goal is to model all of the events that occur in a sequence, so we do not want to disregard anything. So what we decided to do is we decided to use the state-of-the-art model, which is called the epidemic type aftershock sequence model, or ETAS, which basically, so this is the first out of 2 slides with equations, so bear with me. Basically, we start from the background events, which are spontaneous events, and then these events can trigger on their own, which I called here the first generation events. Then these events can again trigger new events, which I call the second generation events, and this goes on until the nth generation. So basically, it goes until the process naturally dies out. This is why it's called the epidemic. So if we want to find the rate of events in a certain time period and in a certain space, we will have the sum of the background rate and of the triggered rate. So no main shock, foreshock, aftershocks. So if we mathematically want to write this, it would look like this. You don't have to think about it. The only important thing is for you to see that the rate depends on the history, meaning that the number of events 1 year from now depends on the events that happen before this time. Okay, so it has memory. It just has memory, basically. And you can also see from these equations that we have a lot of parameters in ETAS. Actually, there are 9 parameters that needs to be estimated. And to estimate the parameters in ETAS model, we need to have good quality data. So we wanted to estimate the ETAS parameter for our case study that we defined in Italy. Basically, we took the instrumental catalog, Horus instrumental catalog that spans from 1981 to 2020, which is a very good quality catalog. We believe in it. And we defined 2 regions in Italy, one in the central part, where we recently seen many, many sequences, so we have a very robust data, and one in the south. And for these 2 regions, so for the central Italy and south, we calibrated ETAS parameters. So we had 2 sets, one in the central Italy, one in the south part, and we wanted to validate these parameters by Turing-style tests. So we basically used the ETAS parameters to generate 500 stochastic catalogs in this time period, so from 1981 to 2020, and then compare them with what actually was observed in this period. So we showed, I'm here showing some of the Turing-style tests that we performed. I'm showing the magnitude frequency distribution and clustering behavior. We also did spatial distribution, temporal distribution, sequence-to-sequence variability, etc. And basically we showed that in both of these regions, the parameters that we calibrated work well. So we are not getting the results that are significantly different. What was very interesting for us is that we noticed that in the south, if we look at the instrumental data, so the earthquakes that happen from 1700s to this day, if we look at this data, we noticed that the parameters that we calibrated based on central Italy actually work better than the one that we have in the south. So this made us think that maybe the parameters calibrated based on Italy are better, so to speak, and they can also work for the south part, because we have a good data in this part of the world. So that said, we wanted to investigate this a little bit more. So what we did is we decided to check what happens if we look at the Croatia. So we collected the data in Croatia, and we had 3 different set of parameters, one based on the data in Croatia, another 2 based on the data in central Italy with some small differences, and showed that actually the results obtained with the central Italy data are more stable. So we did exactly the same with Turkey, and we see the same trend. So basically this means that we, in the regions when we do not have enough data or we have catalogs of poor quality, we can use the data from the central Italy region that are robust. I'm talking about crustal regions. So once we gained confidence in ETAS parameters, we wanted to see what happens if we want to estimate the hazard. So to do that, we defined for case study 2 sites in central Italy, one in Perugia, one in Norcia, and we considered 3 cases. One is the main shock only case, so we do not have sequences. We are using the Poissonian distribution. One is the unconditional case, so we are using the ETAS model, we are considering sequences, but we are looking at the average long-term hazard. So we are looking at the average between the quiet and the active periods. And the conditional case, where we are considering seismic sequences, but we are looking at a particular period in time. In our case, we look at the 1 year after the active sequence that happened in 2016-2017. And you can see on these plots clearly with the blue line that the Poissonian, the rate of exceedance obtained with the Poissonian case is lower compared to the ones that we have with ETAS, both in Perugia and Norcia. And you can see that this is particularly the case if we are having the conditional case. So if we are looking at the year after the active sequence, and in particular this happens for Norcia, because Norcia was closer to the sequence that happened in 2016-2017. So at the end of this hazard part, what we can conclude is that main shock only models are still used in most of the cases, even though they can be quite unconservative, which was showed several times in history. It also showed that the ETS parameters that we have can represent well the seismicity in central and south part of Italy, and we also showed that the ETS parameters calibrated based on central Italy data can work well in south and also in other regions such as Turkey and Croatia. And finally, we showed that the hazard estimates obtained with the ETS model can be significantly higher compared to the main shock only case, and this can be particularly relevant when we are talking about a specific period of time after the seismic sequence. So once we were done with the hazard part, we moved to the fragility and to modeling progression of damage. I mentioned briefly in the introduction that we always assume that the structure is in the intact state, in the pristine conditions, and this is not the case. So sometimes it takes basically decades to repair the building stock. So for example, here in central Italy, I'm showing the damage after the first event and after the end of the sequence, and you can clearly see that there was some accumulation of damage. Even when the damage accumulation is considered, which is very rare, usually it's considered using the non-cumulative EDPs, such as drift, which we believe, and the field observations are showing this, are not working very well when we have seismic sequences or when we have long duration ground motion. So now in the research community, people are starting to use more energy-based EDPs because they are monotonically increasing. So they might work better when it comes to the damage accumulation. So in my thesis, we focused on reinforced concrete buildings, and in particular, I was here focusing on reinforced concrete columns. So we followed this 5-step procedure. We first compiled a database of experimental tests. Basically, we found 370 tests on rectangular columns only that were subjected to cyclic pushover, and from these tests we extracted the relevant information such as point of yielding, cracking, maximum displacement, point of failure, etc. And then we decided to use modified Parkinang damage index as our EDP, so the last slide with the equation. Basically, modified Parkinang damage index has two parts. One is the deformation part, which depends on the displacement, and the other one is the energy part. And within the Parkinang damage index, we have this parameter beta, which needs to be estimated. So what we wanted to do is we first noticed that in our database, we have shear-dominated, flexure-dominated, and flexure-shear-dominated columns. And for every single type of column, we calibrated the parameter beta based on the data that we collected. Once we did that, we wanted to link this damage state, this damage index, to the onset of different damage states. So we defined the damage states, and for each damage state, based on the detailed explanation about the experiments that we have, we proposed the range of the damage index. So for example, we have here one test where we have the point of yielding, which corresponds to damage state 2, let's say. We would calculate the damage index. We'll do this for every experiment, and based on that, we will propose the range of damage indices for different damage state. We then wanted to check if what we are doing makes sense, so we managed to get 23 shake table tests, and we tried to validate our damage index with shake table tests. So I'm showing here one shake table test where we had reported so the authors reported the point of yielding, the point of capping, and point of axial failure. This is the flexure shear dominated column. And basically these are damage state 1, 2, and 3, and for each damage state we would calculate the damage index, which you can see here, and we checked if it predicts well the damage states, and in this case it predicts it well. We then also wanted to see if we use drift, how well it will work, and we noticed that damage state 1 and damage state 3 are well predicted, while damage state 2 it's not. because it's for damage state 2, it's 2.7, which would mean it's damage state 3, and it's not. So we did this for all of the 23 tests that we have, and we noticed that both EDPs work quite well for damage state 1 and damage state 3, but in the case of the damage state 2, drift doesn't work well in more than 70% of the cases. So we gained some confidence into our damage index, and then we wanted to see, to compare it with non-cumulative EDP, with drift, using the damage-dependent fragility curves. Damage-dependent fragility curves, basically, we start from the intact structure, we run the nonlinear time history analysis, we get the fragility curve of an intact structure. So then we have a damage structure, and we do the same, and we get damage-dependent fragility curve. So damage-dependent fragility curve depends on the initial damage state of our structure. So for example, here in this figure, I'm showing the collapse fragility curve in the intact state, and then conditioned on the damage state 1 and damage state 2, and you can clearly see that there is the reduction of capacity. So we derived the damage-dependent fragility curves using 2 EDPs, the proposed damage index and drift, and we did this for 4 SDF systems and for 1 building. And we noticed in all cases that the reduction in capacity is higher if we are using the proposed damage index, so compared to the drift. So for example, I'm showing here for flexure critical single degree of freedom system, I'm showing here with hash the reduction predicted with the damage index, and with the solid bars the one predicted with drift. And you can see that in all cases the damage index predicts more reduction, and it can go for high initial damage state, it can go up to 55%. So basically at the end of this part, we can conclude that our damage index can predict the damage states well, and that if we check what is the reduction of capacity, we see that the reduction in capacity predicted with our damage index is significantly higher compared to the one predicted with drift. Also, what I would like to underscore is that it's not only relevant when we have main shock and aftershock, but also when we have a long duration ground motions where you can have the accumulation of damage. So we talked about the hazard and we talked about the fragility. If we put these things together, what happens? How much does it affect the risk? I'm showing here for 1 single degree of freedom system with a fundamental period of 0.2 seconds, I'm showing the annual probability of exceedance using 2 EDPs, ductility and damage index, and I'm comparing 3 cases. Pausonian case with the gray line, and with the black line, it's ETAS case. But I make a distinction between the 2 cases where we consider the damage accumulation, where we do not consider the damage accumulation. So you can see for both EDPs that the increase due to the hazard is much higher compared to the one that we had due to the damage accumulation. And you can also see that the importance of damage accumulation is more visible when we have the damage index. So for example, here in this figure, I'm showing the ratio between the annual probabilities of exceedance with and without damage accumulation when we use damage index and ductility, and the ones obtained using the damage index, particularly for the lower damage states. So I hopefully convince you that seismic sequences can affect the risk estimate significantly, particularly when it comes to hazard. And then the thing that I didn't talk about yet is the record selection. So now I'm going to talk about record selection, which is a very important part within the risk framework. First, I will talk about record selection in general, so forget for a second about the main shock and aftershock. Record selection represents the link between the seismic hazard and the structural response. So no matter how detailed job we do when it comes to the hazard, and no matter how, if we have a finite element model of a building, if we do not select our records well, it doesn't mean much. So basically what I mean selecting the ground motions well, I mean selecting the ground motions that we expect to see at the site that we are interested in. So hazard consistent ground motions. So for example, I'm showing here exactly the same building located in 3 sites in Turkey, and I'm showing the fragility curves with the solid lines obtained with a hazard consistent approach, and you can see that they are very, very different, even though we have, so for the same level of ground motion shaking, you have very different probabilities of exceedance for exactly the same building if you're located in 3 sites. And with the dashed line, I'm showing the results obtained with IDA, which doesn't consider hazard consistency, which by pure luck matches fragility curve for one side, but not for the other two. It's very wrong. So in order to select the ground motions with the hazard consistent approaches, we need a database of a lot of ground motions, and usually we don't have them, especially in the high intensity range. So what we do is we scale the ground motions. So what we wanted to check is, does the scaling actually affect our results much? So to check this, we defined a quite simple case study. We first collected the database of ground motions. We had a lot of ground motions from all over the world. And we performed the hazard analysis for a site in central Italy, in Perugia, and we defined 10 intensity levels. For each intensity level, we selected the ground motions using the conditional spectrum, which is the hazard consistent method, and we selected 40 records for each intensity level, and we defined 2 groups. One group where we do not have to scale records much, so 1 to 2 scaling factor, and another group where we scale records in the range 7 to 10, so very high scaling factors. And then we run these 2 groups of records on a single degree of freedom system. We defined 5 single degree of freedom systems with periods 0.2 to 2, and we consider 2 constitutive models. And what we showed basically is that in all of the cases, if we select the ground motions in a hazard-consistent manner, the scaling would not affect our results significantly. So it means as long as you select your ground motions carefully, you can scale your ground motions without affecting the fragility estimates. So going back to the aftershocks for a second, when we have aftershock, we have damage-dependent fragility curves that I was mentioning. So things are becoming a little bit more complicated when it comes to the aftershock record selection. I would say that this is the least explored field that I talked about today. Basically, usually what people do is, because the entire interest in cluster seismicity is new, they use the same ground motions for main shocks and aftershocks. However, people believe, and it's been proven, that there is the naturally correlation between the main shock and aftershock ground motions. And what they're saying is that it's important to maintain this correlation because it can affect our results significantly. So there's not a lot of research on this. So what we wanted to do is we wanted to see what is basically the best method to derive damage-dependent fragility curves, and how should we select the aftershock ground motions, balancing the practicality and the accuracy. So to do that, what we did is we defined first the case study. We took again the rock site in Perugia, in central Italy, and we considered only 1 single degree of freedom system. You will see later why. And we took 2 EDPs, the maximum ductility and the damage index, and 2 conditioning IMs. So SAT1, in this case 0.2 second, and average SA. And we did a hazard analysis for a conditional case using ETAS and using Poissonian only model, and we generated 100,000 one-year-long stochastic catalogs. So once we did that, we then wanted to compute the annual probabilities of exceeding different damage states that we defined, using event-based methodology, basically, and using the 3 different methods that I will explain now. And then these methods we wanted to compare with the benchmark. I will explain in the end what was the benchmark. So the first approach is back-to-back IDA. Back-to-back IDA, quite simple. We first perform the regular IDA on the intact structure. We get the fragility curves, then we have the damage structure, and we perform the IDA basically again, and we get the damage-dependent fragility curves. Here I'm showing for maximum ductility and damage index. In this case, no hazard consistency. In the main shock part, we don't think about hazard consistency. The aftershock part, we also don't think about the hazard consistency. Second approach is the approach that was proposed by Papadopoulos in 2020, where they would select the main shock ground motions would be selected with a conditional spectrum, so we have hazard consistency, and then we get the fragility curves, and then we would select the aftershock ground motions, which are correlated with the consistent with the main shock ground motions. So we have hazard-consistent main shock ground motions, and we have aftershocks that are consistent with the main shock ground motions. So we had consistency in both parts. This is an appealing approach. The problem is that it requires often a lot of analysis. It's very hard to get aftershocks in a high-intensity range. So what sometimes happens is that you have unrealistically high standard deviation, and you have this overlap that you can see sometimes in fragilities. So we wanted to see if we can somehow make a balance between these two approaches. So what we did, it's like a hybrid approach where we combined approach 1 and approach 2. So we would select the main shock ground motions to be consistent with conditional spectra and doing the multiple stripe analysis, and we will get the fragility curves of the intact structure. And then we would use back-to-back IDA to see how much the capacity of an intact structure will be reduced when we have the initial damage state. Then we would apply this reduction factors on our fragility curves on the intact building. In this way, we are having the hazard consistency in the initial part, but we are not having the hazard consistency in the aftershock part. We then, I'm the last one. I wait an entire day. We wanted to compare these three methods with the benchmark. The benchmark is the brute force approach. So we do not have fragility curves. We do not have the conditioning IM. What we do is we take 100,000 catalogs that we have with the earthquakes. For every single rupture, every single earthquake, we select the ground motion and we run this ground motion on our building. So we do that for every single building in every single year. We save the damage state of the structure at the end of the year. We do this for 100,000 years and we check what is the annual probability of exceedance. So this is our benchmark. This is obviously crazy from a computational point of view. So that's why we did it for one single degree of freedom system and that's it. And we then compare these cases. The first thing that you will see, the first two figures, is you can see the annual probabilities of exceedance computed with the main shock only approach and with the cluster seismicity. And you can see that the annual probability of exceedance is almost twice as high in the later case. And then in the third figure, you can see the comparison between the ratio between the annual probabilities of exceedance obtained with three different approaches and the benchmark. And you can see the first approach does the worst job, which is the back-to-back IDA, where we do not have hazard consistency, while we are getting the better match if we are using approach 2 and approach 3. What is important here to see is that with approach 2 and approach 3, we are getting very similar results, which means that we can jeopardize on the hazard consistency when it comes to aftershock record selection and go with a little bit more practical approach. So in summary, the main objective of our work was to scrutinize some of the modeling assumptions in risk assessment, in particularly focusing on the cluster seismicity. We showed that we can use ZETA's model to model the cluster seismicity in Italy, and also we showed that we can use the central Italy parameters for Croatia and Turkey. We showed that if we consider cluster seismicity, we will get hazard estimates that are significantly higher compared to the main shock only ones. We proposed the damage index, which we believe it's a good candidate as an EDP when it comes to the damage accumulation. And finally, we talked about record selection. We showed that the scaling records is okay as long as we select them in a hazard consistent way. And finally, we proved that the hazard consistency in the aftershock part is of lesser importance, and that we can use more practical approaches without the loss of fidelity. Okay, because I'm out of time, I will not talk about future research. It's okay, it's okay. Okay, so for the future, what I think is the most important. Okay, thank you. First of all, I think it's important for ETA's parameters to be tested also in other regions in world. I also think that there are several parts of ETA's that needs to be investigated more. For example, the faults are not considered in the model that I'm using. Also, very important is in order to understand the importance of damage accumulation and how can we model it, I think we need more experimental data. If not experimental data, then maybe we can have a very detailed finite element models that we can use to test the effect of sequences. And finally, if we want to use the damage-dependent fragility curves, we need to develop the methods that are requiring less analysis. So that's it. Thank you. Thank you very much.
Thank you, Nevena. And now questions from the committee. Xavier.
First of all, congratulations for the very interesting presentation and for being able to condense so much work that you've done into such a short amount of time. I'm sure it wasn't really easy, but you managed to give a very comprehensive overview of all the work you've done. I will just concentrate on part of your research. I will skip the seismology part because that's really not my field, so I will concentrate on the rest. So first of all, I was very happy to see a topic that was almost dead kind of resurrect. So the study or the research on damage indexes is something I've worked back in the day, a long time ago. And my question on that comes exactly from what I was doing many years ago. So when you were fitting the beta factor on experimental data, I noticed that you tried to fit a constant value. So didn't you try to correlate or establish like an equation for beta as a function, for example, of the actual force ratio or reinforcement or mechanical reinforcement ratio? Have you tried that?
Yes, so I was trying to, well, let's talk for a second about only flexure-dominated columns.
Yeah,
so,
exactly.
Okay, so I was trying with the damage index, I was trying to reduce basically the standard deviation that I have, and I was trying to see, can we correlate it with something else, basically. So the only thing that I noticed, and you probably remember this from Hydra, is that it correlates with the number of cycles. So I have the parameter gamma, which depends on the number of cycles, and it has a very nice correlation. So I also have that in my thesis that I was proposing. This is the only thing that I could see that is correlated when it comes to the flexure-dominated columns. Then for the for the flexure, I didn't see any correlation. For the shear dominated columns, and I'm also have it in my thesis, I have a correlation with the ductility, basically. So there is the parameter gamma that depends on the ductility of a column also. Yes.
The reason why I'm asking that, because this has been done a long time ago, I would say almost 30 years ago. And for, again, flexural dominated columns, there was an expression.
I remember that the beta is a function of, it doesn't change much. That was my, was my problem. It doesn't really change much, and it's, you know.
Okay.
The standard deviation was not reduced much.
So another question about the modeling approach that you followed, because I was wondering if that had some effect, at least when you evaluate the damage index for low damage states. So you didn't mention in the presentation, but you have it in a thesis. So you model the structure and all your numerical models using the Ibarra model, right?
Yes.
But the Ibarra model starts with a cracked stiffness. So you are modeling a structure which is no longer intact because you're already assuming a secant to yield stiffness. So for large damage levels, this has little to no effect, but for low damage states, do you think there will be, maybe some bias in the demand because you are saying that the structure is a bit more damaged than it should be for that level of intensity of the earthquake?
I didn't think about that, to be honest, but I don't think it would affect much. There's entire part in my thesis where I'm talking about the modeling, which I didn't cover here, and I'm talking about Ibarra, and I'm also, I was calibrating Ibarra based on the experimental data, so it was matching the experimental data well, and I doubt that the low damage state would change much in a bigger picture. Particularly if you look at the bigger picture and how much damage accumulation affects the estimates based on what I'm showing compared to hazard, I don't think it's that significant.
So that brings me to my final question, exactly what you just said. So the last part of your research, the record selection procedure, and the comparison that you showed with these three approaches and the benchmark case, and again, keeping in mind that the hazard component plays a huge role in the final results. So do you think that the differences, I'm not talking about the ratio that you showed on the plots of probability of exceedance, I mean, do you think that the difference between the four approaches are that relevant, given, I mean, the end
you
result?
think even if, for example, back-to-back IDA...
So approach one is still okay, right?
What did you say?
Approach one is probably still okay, given, I mean...
Yeah. The difference is less if we use the approach 2 and approach 3, but even with approach 1, the difference is not that significant. Yes.
Yeah, so given the weight of
given that exactly, the hazard component, yes, I agree.
Yeah, okay.
Yeah.
Thank you, and congratulations again.
Sure thing.
Okay, thanks for the presentation. I have two questions.
Sure.
One on the ITAS model, and in particular, the two areas in Italy. So how did you assess the two areas and a different clustering of the two groups that produce different ITAS parameters? Have you done any sensitivity assessment when you were choosing?
How I defined the...
Yeah.
It was very arbitrary. With ITAS, you cannot define... Initially, what I wanted to do, because I was naive, was to define the 10 regions in Italy and then calibrate ITAS for each region, but that's impossible to do because you don't have then enough data in these regions, and ITAS needs a lot of data. So that's why I just defined two big regions arbitrarily, one in the south, one in the central part.
Did you try, for example, if you had assembled the data in a different way, would you have...
Initially I had the central region a little bit differently, and it was the same conclusion.
Okay,
basically. Yes.
Okay. And a second, just a clarification on the damage model calibration. If I understood correctly, you used pseudostatic test as training data set, and then you use basically the shaking table test as if it was a testing data set, correct?
I also had so I didn't put all of the eggs in the one basket, so I didn't use all of the cyclic pushover tests for calibration. I also left some for the validation.
Okay, so it wasn't,
no.
you mixed up the typology of tests.
And I also I try to choose smartly, so not choose just the test with a low axial low axial ratio, but also, have different types of columns for testing. Yes, I did that.
Thank you.
Sure.
Thank you. And thank you for very, very interesting presentation. Now I will back to the seismological part. Okay, but some of the some of the answers that I was looking, you already mentioned in the future work, because I was curious that you are making a lot of good research in the seismology part, but you never mentioned faults. And you estimate aftershocks, main shocks. So, but you already mentioned that you are planning to do in the future works.
So, I'm not a seismologist. So for the faults, there are models with ITAS that incorporate faults. It gets very complicated very fast. So that is something I'm not sure how much it will affect. To be honest, we are using empirical data as a spatial distribution. If you look at the spatial distribution of it will follow the faults. We are getting something reasonable, definitely.
Okay, thanks.
It can also be done in. So now what we are doing, it's not in my thesis, but when we have background events, when they trigger the aftershock events, we can constrain them if they are coming from a fault, the parent event. We can say that the aftershock is also somewhere along the fault, so it can be incorporated in some ways.
Okay, great. And I was curious. Am I right? Am I wrong? You mentioned on 2 slides that Croatia and Turkey have similar tectonic condition.
Yes, in a sense that the clustering behavior the clustering behavior in these regions is similar. Yes.
somebody from the audience will think that it's not so correct. I mean, tectonic,
No,
quite different than, okay.
Yeah.
Okay,
Yeah.
thank you,
Sure.
thank you.
I will try it one more time. Any question from the audience? Okay, so if not, thank you, Nevena,
Thank
once
you.
again.
Thank you.
So let us give the evaluation committee 15, 20 minutes, and then they will come back here. I would ask them not after 6:30 at most, okay, to announce the results.
Pleasure.